Tangent, cotangent, cosecant, and secant. This video will help you understand the graph of y equals tangent of x and y equals cotangent of x, graph variations of the tangent and cotangent of x, understand the graphs of y equals cosecant of x and y equals secant of x, and then graph variations of the cosecant and secant. Alright, let's start talking about the tangent of x here. So the graph of tangent of x, and as a reminder here, tangent of x is sine of x over cosine of x. And I've given us a unit circle here so we can kind of look at the values and see what happens here to create this one period of the tangent of x over here. So let's start with 0. An angle measure of 0. Let's start with an angle measure of 0. If I put an angle measure of 0 in here for x, then my x-coordinate will be 1 and my y-coordinate will be 0. So y-coordinate, of course, is the sine of x, and x-coordinate, of course, is the cosine of x. So at 0, we get a value of 0, and you can see that right over here on our graph. Right there. At the origin, we're going to pass through the point 0, 0. So now, as we move up the unit circle here, notice sine of x is starting at 0 and increasing up to 1. So our function is going to increase, and not at a very quick rate. It's going to kind of increase at a very slow rate here till we get right to about here, right to about that point, and then it's going to start to grow rather quickly. Because what happens from here over now is our x-coordinate is approaching 1, which means the cosine of x here, our x-coordinate is approaching 0. And our cosine then of x is going to be also approaching 0. And ultimately we're going to approach this scenario where sine of x goes to 1, cosine of x goes to 0. Well, when cosine of x actually goes to 0, we're going to get undefined and we're going to get this asymptote. And you can see that right here. Here's our asymptote at pi over 2. As we get close, as the cosine gets close to 0, we're going to get very, very tiny values that we're dividing something that's close to 1 by these very tiny values. So this graph is taken off to positive infinity there. Something happens similarly if we travel now in the negative direction, starting out again at a value of sine of x of 0, cosine of x is 1, so we start out, same place we started out as before, at 0 here. Now we are going to grow, but in a negative direction, until we get down to here to negative pi over 2. And at negative pi over 2, we're going to get the same scenario where our cosine of x is 0, our sine of x is 1, and so we end up with another place that's undefined. We get this other asymptote. And as we're approaching this asymptote here, we're going to be dividing by very, very small values here, a negative number by very small values. So this guy's going to take off to negative infinity. And this is our normal period of the tangent. We go from negative pi over 2 to positive pi over 2 to give us this one graph of the tangent. Notice this tangent graph is a little different than our sine and cosine. Our sine and cosine usually was bounded between 1 and negative 1, or whatever our amplitude was. This thing is taken off to both positive infinity and negative infinity. All right, let's take a look at some characteristics of the tangent function. Tangent function is odd. Its period now is just pi. Notice if we graph repeated cycles of this is the graph we looked at from negative pi over 2 to pi over 2. That is a distance of only pi. So the tangent repeats itself every pi, unlike the sine and cosine, which had a period of 2 pi. You can see we get this same graph repeatedly as we travel every distance of pi. The domain, remember in sine and cosine we had an unlimited domain, but here we can't have these multiples of pi over 2. In fact, odd multiples of pi over 2. We could have even ones. Even multiples of pi over 2 end up being whole numbers like here 0 and pi and 2 pi. Those values are always going to be 0. But at these odd numbers, 1 pi over 2, 3 pi over 2, 5 pi over 2, we're going to have asymptotes. the range, we're going to get all real numbers, negative infinity to positive infinity. All right, now let's take a look at the graph of the cotangent of x. Very similar to the graph of the tangent of x, except now we're reversing this. Cosine is on the numerator, sine is in the denominator. So we're going to get our places where it's undefined when sine of x equals 0, which is going to be right here and right here. So at 0, we're going to have an asymptote. So there's an asymptote right here at a coordinate of 0. And then over here when we get to pi, we'll also have an asymptote, and that's what you see right here, another asymptote going right there. Now, the cotangent function, our period of this is between 0 and pi. So tangent was negative pi over 2 to pi over 2. Here, one period of the cotangent, we start at 0 and we go to pi. And notice the tangent traveled in a negative direction up to a positive direction. The cotangent does the opposite. We travel at a positive direction. Then when we cross pi over 2, we travel in a negative direction. Reason being that here, as we get close and close to 0, we're here positive. We're getting close and close to 0, and both values are positive, and that's why we're taking off here to positive infinity. But when I start approaching 0 for the sign over here, notice I'm on the negative values. Once I cross over this pi over 2 here, my x coordinates now are all negative, and that's why we get these negative values here for the graph, and we approach that negative infinity. Okay, the vertical asymptotes, remember with tangent, they occurred at pi over 2 or odd multiples of pi over 2. Here, these are going to occur at multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi, and so on and so forth. Just like the tangent, our x-intercepts are occurring halfway between my asymptotes, and that makes it easy really here to graph these things, because we need to, just like before when with sine and cosine we found those 5 key points, we're going to find 5 key points for the cotangent and tangent. 2 of those key points are the asymptotes. One is halfway between, and then just like with sine and cosine, this value here is a quarter, and this one is 3/4 of the way, these 2 points right here. And that's where the graph really starts to take off and either approach infinity or approach negative infinity. It moves kind of slowly between these 2 critical points, but then it takes off here. And that's why we have those as part of our key points in making this graph. Odd function, origin symmetry, I already talked about 1/4 and 3/4. Let's talk about this though. These values, these key values here I talked about, these 1/4 and 3/4 values, those will always take on the value of a. So if I have just cotangent of x here, notice the value of a, which is my value out front, is just 1. So those values will take on 1 and -1 respectively. If I had a value of 2 or 3 out here, then these points would climb all the way up to 2 or 3 before it starts taking off. All right, variations of the tangent and the cotangent. So they're almost identical, tangent and cotangent. The variables in there, you know, a, b, and c are going to all be the same. The only difference is that when we go to find our asymptotes by finding the beginning and the end of one period, the only difference here is that the tangent, we start at negative pi over 2 to pi over 2. Cotangent, we go from 0 to pi. That's because this is the normal period for the tangent, negative pi over 2 to pi over 2. This is the normal period for the cotangent, 0 to pi. Just like when we were doing the sine and the cosine, we started with our double inequalities here with 0 and 2 pi because those were the normal periods for sine and cosine. So other than that, graphing the tangent and cotangent are almost going to be identical. We already talked about this a little bit. The x-intercept is midway between the asymptotes, and then our key points 4 and 5 are 1/4 and 3/4 of the way between those asymptotes, and those coordinates have a y-coordinate value of -a and a. Talked about that a little bit in the last slide. All we do then is use steps 1 through 3 to graph one full period of either the tangent or cotangent, and then if we're asked to add another cycle, all we have to do is repeat that cycle again to get the second period. All right, let's take a look at this again. So here's a graph of the tangent here. Let's talk about these things. Our asymptotes. We go ahead and solve the double inequality to find our two asymptotes. Midway between, we'll cross the x-axis, and then 1/4 of the way across, we get this point, and that value is negative a, whatever our a is out front here. That's a negative a, and then this value here is a positive a. And that's, again, this is 3/4 of the way across our graph. So really, finding this spacing and finding these key points is very similar to finding the sine and the cosine. All right, let's take a look at an example now of graphing the tangent. So we want to graph this tangent here, y equals 3 tangent of 2x, and they want us to graph it on this interval from negative pi over 4 to 3 pi over 4. Okay, so first thing we do is we take a look and we get our a, our b, and our c. Once we find those values, then we want to set up our inequality. So notice for tangent right here, the normal period for the tangent, as I said before, negative pi over 2 to pi over 2. All we do is replace whatever we have up here in the center. In this case, it's just 2x, so I'm putting 2x in the center there. We're going to solve this for x, multiply everything through by a half, and we see then that the asymptotes, or the beginning and end of my one period of this graph, is going to be from negative pi over 4 to pi over 4. Okay, once we've identified the asymptotes, that's 2 of our key points there. Now we need to find our other key points. So let's see, I'll just draw a little sketch here. So I got my graph, and I know that I have one asymptote over here at negative pi over 4. And I have the other one at positive pi over 4. Okay. So now what we want to do is we want to find the midway between these 2 points, because that's where our graph is going to cross the x-axis. Well, if we're at negative pi over 4 and pi over 4, midway is right there. So that's where our graph is crossing the axis. Now I want to find 1/4 of the way and 3/4 of the way. Well, if this distance from here to here is pi over 4, half of that will be pi over 8. So this will be negative pi over 8. Same thing over here, distance of pi over 4, this distance will be just pi over 8, positive pi over 8. Okay, so I know the tangent starts negative and rises up positive. I need these values to be my value of a in front. So let's see what my value of a in front is. That's 3. So I go 1, 2, 3, 1, 2, 3. And so at my negative pi over 8, my graph is going to go through that point. And at my positive pi over 8, it's going to go up 3 units there. So my graph now comes up and curves, and then once it hits that point, that critical point, that's where it starts to take off and go to infinity, and then here take off and go to negative infinity. So there's a graph of one period of that. I think they wanted us to graph a couple more periods than that, and I have that in the next slide here. Okay, so they want us to graph from negative pi over 4 to 3 pi over 4, which means we're just going to include one more period. So here was the one that I already made, and then here's the second one. We would also want to label these points. We would want to make sure on our graph we had these points labeled, that this was at negative pi over 8, this was positive pi over 8, and that we're at a value of 3 here. 3 here, we'd want to include that. We would want to do the same thing here. We'd want to make sure we included those values. So if this was a problem that we're doing, or a test or something, or a quiz or a section check, we want to make sure that we include these critical points and also label those as well. All we'd have to do is take pi over 4 here and add pi over 8 to it. Pi over 4 plus pi over 8, that's 3 pi over 8. And then here we take pi over 2, add another pi over 8 to it. Well, that's 4 pi over 8, that'd be 5 pi over 8 there. So again, we want to make sure we include those points as part of our 5 key points in our graph. Okay, variations of the cotangent. really similar. Notice that the cotangent starts positive, then goes negative. These key points are the same way across. This coordinate is 1/4 of the way across. My center here is 1/2 of the way across. And this point there is 3/4 of the way across. I find the asymptotes almost exactly the same, except in my double inequality now, instead of negative pi over 2 and pi over 2, I have 0 and pi. Let's go ahead and try a practice problem, and we'll kind of work it in steps here. So we're going to graph y equals 1/2 cotangent of pi over 2 of x. So let's start by finding the asymptotes. And notice with cotangent, our normal boundary points are 0 and pi. So go ahead and pause your video. Go ahead and pause your video player now and just get the asymptotes down. All right, so we've got 0 less than pi over 2x less than pi. One thing to note too here, I haven't mentioned this yet, but it's something I need to mention. Notice we've got strict inequalities here. With sine and cosine, we had less than or equal to, less than or equal to. The reason is, at these values, pi and 0, we get our asymptotes in our normal cotangent graph. And whatever we solve for here is going to be our asymptotes in our new graph. And of course, we can't include the values at the asymptotes because that's where the graph is undefined. All right, so I want to get rid of this pi over 2. So I'm going to go and multiply by its reciprocal, which is 2 over pi. So let's see, I multiply here, 0 times anything is 0, less than. We already said this is going to divide that out. So we'll be left with x there. And here, if I think about this, 2 over pi times pi over 1, that's going to divide those pi's out for me and leave me with just 2. So it looks like my asymptotes are happening at 0 and 2. So if I was to sketch my graph there, there's 0. I put an asymptote there. And then 1 out here at 2. So 1 and 2. All right, let's go on to the next step. Okay, we got asymptotes at 0 and 2 as discussed. Now, let's go ahead with steps 2 and 3. Find the midway point for our x-intercept, and then find the 1/4 and 3/4 places for my values of a and negative a to go on my graph, where the thing really starts to take off in either a positive or negative direction. All right, go ahead and pause your video player now, and let's finish this graph. Okay, so we already had points at 0 and 2, as discussed. Asymptote at 0, asymptote at 2. So this is going to be 1. That'll be our midway point. And then 1/4 of the way would be a half here. 1/4 of the way would be a half. 3/4 of the way would be 1 1/2. All right, so to sketch this guy out then, it looks like, let's get some values on here for our x-axis. We're only going to be going up a half here, so let's say here's 1, here's 2, 1, 2. So over here at this key point, we'll be going up just 1/2. And then over here at this key point, we'll be going down a half. And then remember the cotangent starts positive and then goes negative. So a sketch of your graph should look something like that. Okay, and here's a bigger blown up version of it. It's all pretty. Again, this is something I get from the publisher here, so I don't have to make these graphs, but they need to include these values. Notice, you see they've got just kind of a generic pi over 4 and a pi over 2. We need to actually have the values of this coordinate there. We said that was 1, this was 2, this was 1/2, this was 1 1/2. And then we also need to include these values here because this was another one of our key points there. And those were happening at 1/2. So we need to make sure we label those on our graph as well. The graphs of y equals cosine of x and y equals secant of x. We obtain the graphs of cosecant and secant curves by using the reciprocal identities. So remember, the cosecant is equal to 1 over the sine. The secant is equal to 1 over the cosine. So in order to make these graphs, what we do is we start out by just graphing. If we're going to do the cosecant of x, we're graphing the cosecant of x, we start out by just graphing a quick sketch of the sine of x, since cosecant is equal to 1 over sine of x. If we're trying to graph the secant of x, we start out by just graphing a brief sketch of y equals cosine of x. And we already got a lot of practice graphing cosine of x and sine of x. And really graphing the secant and cosecant is not much more difficult than that. We really just add one more step to graph the cosecant and secant. And so as discussed, so cosecant of x is 1 over sine of x. And so you can see here, let's see on this graph down here, let's look at this graph. Let's find our 0 here. Here's the graph of our sine of x, normal sine of x. Starts at 0, climbs up, comes down and around like that. Okay? So what happens here when sine of x starts out, it's at 0, notice. And so if I have a 0 in the denominator here, I'm getting an undefined situation. So that's where my asymptote comes in. So just like with tangent and cotangent, we have asymptotes. In fact, every time sine becomes 0, we're going to get an asymptote. And you can see these listed, and that's happening every pi. Every pi we're going to get an asymptote. And so as the sine starts to get really small, getting closer to 0, we're going to be dividing 1 by a very small number, which means this guy is going to take off to positive infinity. And you can see our graph here, nice parabola, taking off to positive infinity. And then same thing happens here as I approach this asymptote of pi, taking off to positive infinity. Once I cross pi now, I'm going to start getting negative y values or negative sine values. So this guy's going to be taken off to negative infinity over here. And so really graphing the cosecant is as easy as graphing the sine. Every place the sine goes to 0, create an asymptote. Every place the sine reaches its maximum value, that's going to be the vertex of our parabola then. Or whenever our sine reaches a minimum value, that will be the vertex of our parabola. So you graph the sine, graph the asymptotes, and then just graph the parabolas using the peak of the sine curve as the vertex of the parabolas. Secant of x has the same period as the cosine of x. It's 2 pi. The domain is all real numbers except odd multiples of pi over 2. Okay, so cosecant of x has the same period as the sine of x, which is 2 pi. The domain is all real numbers except every place that the sine goes to 0. And the places that the sine goes to 0 is multiples of pi. Notice I start out at 0, 1 pi, 2 pi. So those are all the places where our cosecant is going to be undefined. The range is kind of interesting here because notice we don't get any values between 1 and negative 1. So whatever my sine curve is, those values are excluded. If I had a bigger amplitude, like sine was going between 2 and negative 2, then those values would be excluded too. So we would say all real numbers such that y has to be less than or equal to negative 1. So one of these two ways. You can say y is less than or equal to 1, or y is greater than or equal to 1, or we would say negative infinity to negative 1, positive 1 going off to positive infinity, but again excluding those values between negative 1 and 1. All right, let's take a look at some of the characteristics. As discussed, the vertical asymptotes appear at multiples of pi. It's an odd function, so if we have the cosecant of negative x, it's going to be negative of that. It has origin symmetry. All right, now let's talk about the secant of x. Very similarly, except now that we're dealing with 1 over the cosine of x. Our period is 2 pi. Our domain is all real numbers except where the cosine of x goes to 0. And you'll notice the cosine of x goes to 0 at odd multiples of pi over 2. So if I start here at 0, the first 0, I don't have a 0 there, but I have one at pi over 2, 3 pi over 2. then 5 pi over 2, 7 pi over 2. Those are all the places that the cosine goes to 0. So those are all the places I'm going to get an asymptote here. And just like with cosecant of x, all we do is find the peak or the valley of the graph of the cosine, and that's the vertex then of our parabola. So secant of x looks very similar to the cosecant of x, except our parabolas are just in different locations. And just like before, the range is all real numbers, except we got to exclude those values between 1 and -1. So we could say it this way: less than or equal to 1, greater than or equal to 1, or with our notation, negative infinity to -1, including the -1, and then +1 off to positive infinity. Okay, as discussed already, vertical asymptotes at odd multiples of pi over 2. It's an even function here. The secant is an even function, so if I take the secant of -x, it will give me secant of x has y-axis symmetry. All right, let's take a look now at an example of using the sine curve to obtain a cosecant graph. So we want to graph this guy. Let's say this was our question here. Graph y equals the cosecant of x plus pi over 4. Well, to do that, what we're going to do is we're going to first start by graphing the sine function with the same a, b, and c in it. So we've just got the sine function of x plus pi over 4. So we would use our skills then to graph, this is the sine function of x plus pi over 4. And as discussed, everywhere we cross 0, that's going to be our asymptotes. And then all we do is find the peak and the valley of our sine function here. And then from there, graph our parabolas. Let's go ahead now and practice graphing the secant function. So we want you to graph this function between -3 pi over 4 to 3 pi over 4. And so the way we do this is, if we're given a secant function to graph, well, we start with the corresponding cosine function. So go ahead and pause your video player now and go ahead and graph this cosine function. When you get done graphing the cosine function, put in your asymptotes, put in the vertex of the parabolas, and then go ahead and sketch out the parabolas. Hit play when you're done to see how you did. All right, let's see. So let's start in here. We know that a normal period for the cosine is 0 to 2 pi. And that 2x is what we're taking the cosine of. So I'd solve this, divide by 2. So it looks like one period of this guy is going to be pi. So we'd sketch this out. And we'd say, okay, it's all happening at pi, so I'm probably going to stretch my graph out a little bit. Just like with all of our other trig functions, we got to split this up into 4 parts. So first I'll take half of it, which would be pi over 2. Then I'll take half of that, which would be pi over 4, and then 3 pi over 4. So there are my critical points. Now remember that cosine starts at 1. When we have an angle of 0, it starts at 1. Although here, let's look at this. Notice we've got an amplitude of 2 here, so I'm not going to be starting at 1. I'll be starting at 2. 1, 2. So I start there. Then I travel down to 0. And then I travel down to -2. Travel back up to 0. And then finally back up to 1. Now they wanted us to kind of keep going here. So we're supposed to go from -3 pi over 4 to +3 pi over 4. So I'm going to continue my graph going this way. See, I'll just go over here from pi, split that in half. And then the same values are just going to be negative over here now. So those are all going to be negative. Okay, so let's see. Continuing on the same here, this is going to come down and then go to -2, back up, and then finally complete the cycle. So now let's go ahead and sketch in the graph of the cosine here. Okay, every place the cosine becomes 0 is where we're going to get our asymptotes. Okay, and then every one of these peaks or valleys will be the vertex of our parabola. So here's the vertex of our parabola. Here's the vertex of our parabola. And if we wanted to, we could graph just half of that one there. I guess since it goes to pi. Same thing here. Okay, so a lot of times you'll see people here use a different colored ink to indicate this is the graph of the secant. This here is really not part of the graph of the secant. So sometimes people will use a different colored ink, or also sometimes people will just use, a dotted line, which is a lot easier apparently to make with a pencil. So you could just go through and erase some of that. So you make a dotted line, or just as you're graphing those points, make a dotted line. But you want to make it clear to your reader that these parabolas are the graph of the secant, and that this is just a tool. The graph of the cosine here is just a tool for you to find those values.